Hi, thanks for watching. The title of my project is Predicting Tropospheric Ozone Levels from Historic Data Using Machine Learning. What's ozone? Well, ozone is occurring oxygen that has an extra oxygen atom, which is O3. It occurs when certain atmospheric conditions occur when we have low humidity, a lot of sunlight, high temperatures. This is historically when we have hot sunny days, and you've received ozone alerts. We've all had them, and we know what they are. But how are they formed? Well, we have NO2, which is not normally occurring in the atmosphere. It's mostly produced by burning fuel. Matter of fact, 87% of the air's NO2 is produced by burning fuels, and most of that's produced by automobiles and trucks. What happens is when the sun comes up, it sends ultraviolet rays. In low humidity situations, it causes an oxygen atom to be released from the NO2, and it comes floating free and looks for a new home. Oxygen by itself, without attached to something else, is very unstable. It finds the O2 and it loosely couples to those O2s, and now we have O3, which is smog. It occurs against the tropospheric layer, which is very close to the Earth's surface. It's very uncomfortable for most people to breathe, and we don't like it very much. It's smog. Fortunately, at night, when the air cools and the humidity goes up, the oxygen again releases, and it goes floating around looking for some place to go. And there's the nitrogen with the single oxygen. It couples back up again, goes back to nitrogen dioxide. Unfortunately, it's now a precursor again for the next day. But so basically, we have precursors, O2 and nitrogen dioxide, and we have atmospheric conditions. Since we know the atmospheric conditions, they're quite predictable, and we know how much atmosphere pollutants we have, we should be able to use machine learning to predict whether smog will be created or not. So what we did is we took our data set, which was captured from the EPA, a 3-year data set of hourly NO2 and O2, or O3 actually, samples in Cincinnati, and weather for that same 3-year period, hourly information from a place called MetaBlue, which supplied us with hourly data, which we took from mostly temperature, pressure, cloud cover, and sunshine. We can see these are just 5 of those variables we looked at. We looked at temperature, pressure, relative humidity, sunshine, O3 and NO2. And you can see the O3 as it goes up and down along with the sunshine. And with the NO2, it reverses that same course. As that oxygen is released from the NO2, it joins up with the O2 and becomes O3, and then it goes back in the cycle. And you can see that diurnal cycle that goes along with the sunshine. What we did is we took our model and we decided we would do 2 different experiments. First, we want to know, can we predict the next hour based on these inputs? And can we predict what will happen the next hour of the ozone production? And then we'd also like to know, can we predict the next 24 hours based on the previous 24 hours? First, we fed our information into a linear model. We're going to use 3 different models. We're going to use a linear model, a convolutional neural network model, and a recurrent neural network model. First, we fed into the linear model, which is going to be our base model. And then we took a look at the kernel values to see which of the input variables had the largest effect on predicting the ozone during our testing phase. And we found, not surprising, that sunshine and temperature were the largest factors. This is very consistent with what previous work reported. What we did find remarkable is that clouds had such a remarkable effect, because really clouds haven't been recorded as being particularly remarkable in their effect on the overall phenomenon, especially low clouds having a positive effect on the production of ozone, which is somewhat counterintuitive. There is some interesting research about whether or not ultraviolet light can be intensified by the presence of clouds, but it also is possible that maybe the low clouds are actually the ozone being reported. We're not really sure of that. So for now, we're just going to leave that for another research question. But this is consistent with what we expected, to see a lot of sunshine, a lot of temperature, and of course, Also, the relative humidity in a negative way, having the most effect on the production of ozone. So first, our next hour model, and this is the results from the linear model. And we expect a linear model to be at least halfway decent predicting the next hour's production. The pink is the actual occurrence, and the blue is the predicted. And the linear model does what you would expect a linear model to do, which is to stay pretty close to what the actual values are. The next model, this is the convolutional neural network. And it does, as you see, it does a pretty good job of following that pink line. Actually, quite good job. It follows it all through that first 24 hours, and then it does a very good job of predicting that next hour as well. And now the recurrent neural network also does a fairly good job of predicting the 24-hour period and a good job of that last hour. About the same as a convolutional neural network. And these are the error values that we receive, root mean squared error values that we receive for each of those three models. And the LSTM actually performed the best. Not too surprising, actually. That's about what we'd expect. Next, this is the models performing on a 24-hour period, predicting the next 24 hours. This is the linear model, which doesn't do particularly well at all. The pink being the actual reality, and the blue being its prediction. It just pretty much drew a straight line, which is what you'd expect it to do. This is the convolutional neural network, which does remarkably well. You'll notice the first entry, it doesn't do so well, and even not so well in the second, but does better on the third. I believe the reason for this is if you look at the first, the normalized numbers are not very broad. They're not very extreme, and the same for the second. So I think that the reason this is doing so poorly is that it's almost noise at that point. So it's not doing very good at predicting noise. We probably need to regularize this data a little bit better to put away that noise. We should probably do that for the next round. This is the recurrent neural networks behavior. It did not too bad. It did very well on the third, where there was actually a good diurnal behavior. I didn't do so well on the first one or the second one, which again was more of the low, almost noisy response. This last one is an aggressive autoregenerative recurrent neural network, which is something that TensorFlow recommended we try. It didn't do particularly well at all, so it just probably wasn't applicable for this requirement. And this is how they did, the four models did. Surprisingly, or maybe not surprising, convolutional neural networks did the very best. My experience has been from deep learning is that convolutional neural networks are very difficult to beat in most cases. It could be that the LSTM didn't do well because of certain data conditioning that we didn't do. So probably warrants doing a little more research. But it is quite effective. I think that the low mean scores are good. And I think that the convolutional neural network was very effective at predicting ozone, and it is worth going forward with the same model. Thank you very much, and have a good day.